Some things we already know, like we know that we have some function f of x, that all of these functions do have this thing called the derivative. And the first definition of the derivative is that the derivative at a certain value represents the slope of the tangent line. And so the first topic we're going to look at today is how can we actually find that exact equation of the tangent line, and then see the different applications we have from there. So all the rules that we have learned are going to kind of show up today. I did choose kind of some easier problems just for the sake of time. But we're going to look at these tangent lines. So the first thing we know is that the slope of the line tangent to the graph of f at x is literally the derivative. So taking that first statement, we see the slope of the line tangent to the graph of f at x at a, we can shortcut that whole statement by writing it as f prime of a. The derivative of a is the same thing as the slope of the tangent to the original function. And we can use that to actually find the slope of the actual line. So calculus in many ways, especially this first unit, I think of like, it's really just algebra 1 stuff, but on steroids. And back in algebra 1, you learned about the point slope equation of a line. And the point slope equation of a line was written as y minus y1 is equal to m times x minus x1. Hopefully that looks a little bit familiar to you. And we're basically using that same formula in calculus. I could leave it written like that, but typically in calculus we'll write it a little bit different. And in calculus we'll write it as, we still have the y. Instead of writing m, we'll talk about that as the derivative at a. And then I have x minus the a value. And then we have y minus, the y value is going to come from f of a. So we can use that to actually find the equation of a tangent line. So looking at the second question, we're not quite at the tangent line yet, but if I do want to find the slope, some things that we do want to make sure we're careful with is you don't plug in your x value until after you find the derivative, or else you're really just taking the derivative of a constant. So if I want to find the slope of this equation at 2, you first want to find the derivative. This is just going to be the power rule. The derivative of 3x squared is 6x. The derivative of 2x is 2, and then 3 is a constant. So what is the derivative at 2? The derivative at 2 would then become 6 times 2, 12, plus 14. To put this back into some context of what that actually represents, so 3x squared plus 2x minus 3 is some sort of quadratic. And what we're basically saying is at the x value of 2, there is a tangent line. And the slope of that tangent line is 14. So we know that it is increasing at 2, and also that the graph is fairly steep at 2. So to use that slope, if I want to write the tangent line at 2, I'm going to go ahead and rewrite the equation. We're going to think of the equation of a tangent line as y minus a y-coordinate equal to the slope at a times x minus the x-coordinate. And that's the equation of a tangent line at any point. We already found the slope. We saw that f prime of 2 was 14. To find the y-coordinate, we always do plug it into the original function. I did adjust this once. Let me go back and find it. Getting ahead of myself. So now I want to find the derivative at 3. The derivative at 3, that will become 6x plus 2. The slope at 3 would be 6 times 3 plus 2. So that's going to be 18 plus 2. It has a slope of 20 at 3. The y-coordinate at 3, plugging it into the original function. And so that gives us 3 times 9 plus the 6 minus the 3, so 30. So So the equation of the tangent line using the point slope version of the equation is I have y minus the y coordinate is equal to the slope and then x minus the x coordinate of the point of tangency. You can leave your equation in that form. Obviously, if you wanted to simplify it, you would distribute the 20 across and then add the 30. But again, conceptually what you found is there is some point, which happens to be the point 3, 30. And at that point is a tangent line, and the equation of the tangent line is what we just found. Which has some other applications. Today we're going to mainly focus on like finding the tangent line and using the tangent line. But that's basically how we're going to find tangent lines in this class. Any questions on any of that? All right, so we have tangent lines in calculus. We also have normal lines. A normal line is a line associated with the graph, but a normal line is a line that is perpendicular to the tangent line. We can often use the upside down T to represent perpendicular. And so visually, if we look at a graph, I'm going to go back to kind of that same quadratic. We were dealing with this idea of finding the tangent line, which we know is coming from the derivative. The normal line, which has its own applications, is a line that is perpendicular to the tangent line. So it hits the function basically at a right angle. So again, also to review some things about that we use in calculus from Algebra 1. If a normal line is perpendicular to a tangent, how are the slopes going to be related to each other?
They're inverse?
Inverse, we often describe it, so perpendicular slopes are, and we often use the phrase opposite reciprocal. I probably want to use inverse because that has some other meanings in math, but opposite reciprocal, which means basically we like flip the fraction and then change the sign of that number. The steps to find the equation of a normal line are basically the same as a tangent. You still need the derivative. You still need to plug in the value of the derivative to find the tangent line's slope. Flip it and change the sign, and then plug it into your point slope form of the equation. So I have find the equation of the line normal to f at x equals -1. So we first want to find the tangent slope. So we'll find the derivative, which we've already found twice before. I'm going to find the tangent line's derivative at -1. 6 times -1 is -6, plus 2 is -4. So again, that is the tangent slope. Since we're looking for the normal line slope is going to be the reciprocal of that and change the sign. Well, the reciprocal of 4 is 1/4. This was negative, so the normal slope would become positive. And then we still need a y value. Again, the y value is always going to come from the original function. So that's going to become 3 minus 2 minus 3, which is just going to give you -2. So finding the equation of the normal line, I have y minus the y coordinate, which is equal to the normal slope times x minus the x coordinate. And again, if you don't like all those double negatives, then of course you could simplify it. You can simplify it further by distributing the 1/4 across, but there's really no need to. If you're comparing this to the actual tangent line, so I didn't ask us to find it, but if we did want to find that tangent line, the line tangent to the graph would basically be that same coordinate, that is the same point of tangency, but we would have used the original slope given to us by the derivative. So we have tangent lines, and then we also have normal lines. Questions so far? All right, so finding tangent and normal lines are pretty straightforward. Like you find the derivative, and again, any rules that we've learned can show up. So like the trig rules, product rule, quotient rule, rewriting the problem first and then find the derivative, all those rules still apply. But the process is pretty easy. Plug in the x value into the derivative, plug in the x value into the function, and then use that to write the equation of a line. All the other examples we are doing are going to be kind of like applications of this idea of the tangent. And the first application I want to look at is a horizontal tangent line. So I have this function where y is equal to, and then there's like this 6 plus x to the 5 halves over x to the 3 halves. And we want to find the horizontal tangent line. Finding a horizontal tangent line is one of the most common skills we see over and over in this class. Like we'll do it a lot in unit 3 and a lot in unit 4. And that's because in different contexts, we're going to see that we can interpret horizontal tangent lines a lot of different ways. So looking at this, if I'm asking to find at what coordinates does this graph have a horizontal tangent line, what does it mean if I say horizontal tangent line? What process are you basically going to have to go through?
We're gonna have to find out
slope
when
is 0.
the derivative is 0.
When the slope is 0, the derivative is 0. And so that's what I'm going to kind of emphasize. If you see horizontal tangent line, that means the derivative is equal to 0. And there's kind of like, it's not really a joke, but if you're in calculus, especially like the first half of the course, like if you don't know what to do for a problem, 8 times out of 10, you're probably going to take the derivative and set it equal to 0. And that's why finding a horizontal tangent line is a pretty good skill to have. And so then let's talk about finding the derivative. So as this function is written right now, you would need to use the quotient rule. And I don't want to say that that would be wrong if you use the quotient rule. The quotient rule though just is really messy. Like you have the low d high, less high d low, draw the line and the bottom squared will go. So like it's a very messy problem, especially if you're thinking ahead and saying, okay, so I'm going to find the derivative and then set it equal to 0 and solve. So if we can make this a simplified problem first before we take the derivative, it's going to make your life a lot easier when it comes to the actual solving. So to emphasize again, you can take the derivative like this is written, or if you're kind of thinking smart about it and saving time, you might notice, well, hey, this is being divided by a monomial, which means I can take that problem and split it up into, in this case, 2 separate fractions. And in doing so, you can simplify that problem and then hopefully avoid the quotient rule. So I have y is equal to, that is going to become 6x to the negative 3 halves plus, same base, so you subtract the exponents, 5 halves minus 3 halves is going to give you 2 halves, which is just 1. So that second term is just going to become x to the first power. Don't make the mistake and set the function equal to 0. We want to find when the derivative is equal to 0. So now we can go ahead and find the derivative. I am going to label it y prime now. So this first term is going to use the extended power rule that negative 3 halves comes down in front. So I have negative 3 halves. The 6 was a coefficient. Negative 3 halves minus 1 is negative 5 halves. The derivative of x is just going to give you 1. Cleaning that up a bit, 6 divided by 2 is 3, so we get negative 9 x to the negative 5 halves plus 1. So that's the first step we need to do. We find the derivative, and now we want to find our horizontal tangent line. So we're going to set our derivative equal to 0, and then solve. And this is where those prereq skills come into play. So when I say solve, any type of equation you've ever solved before can show up in the derivative. It could be a trig equation, it could be, we haven't learned them yet, but it could be an exponential or log equation, it could be a polynomial, it could be a simple linear equation, but basically we want to take that and use our algebra to solve it. Different ways you can go about solving this one. I'm going to go ahead and subtract the 1 from both sides, and then I see that the negatives end up dividing out. And then cross multiplying, we get x to the 5/2 is equal to 9. How do we solve this and cancel out an exponent to the 5/2? Well, we can raise both sides to the reciprocal of that. So I can raise both sides to the 2/5. So we do see, where does this graph have a horizontal asymptote? This graph has a horizontal asymptote at 9 to the 2/5 power. If this was an even root, so this is a 5th root, we would need a plus or minus. Since this is odd, we don't have to worry about the plus or minus. If you don't like those fractional exponents, some other ways you could write it. You could write this as the 5th root of 81, or you could write it as the 5th root of 9 squared. All three of those answers are technically equivalent. And then you do always in calculus make sure you go back and actually answer the question being asked. So this one did ask for at what points x comma y. So we do want to write the actual coordinate. This graph has a horizontal tangent line. But we see that the x coordinate is 9 to the 2/5 or any of those equivalent answers. The y coordinate, I have 6 plus whatever x is raised to the 5/2 all over what x is raised to the 3/2, and x again was 9 to the 2/5. If you left your answer like that on a test or a quiz, I would honestly give that full credit. On the AP exam, this is probably going to be a multiple choice question though, so you do want to make sure you have the skills to simplify it. This one simplifies somewhat nicely. So we have 6 plus 9 to the 2/5 raised to the 5/2 is just 9. Power to a power means you multiply. And then 9 to the 2/5 raised to the 3/2 is going to become 9 to the 3/5. And so a simplified answer might look like this, which isn't much simplified, but that's about as far as we can take it. Main idea from this slide I want you to get is horizontal tangent means take the derivative and set it to equal to 0. When it comes to partial credit, the AP exam always awards partial credit for free response questions. Every problem guaranteed like this is usually more than just finding a horizontal tangent line, but you usually earn partial credit for finding the correct first derivative and just showing that it's set equal to 0. So you do want to make sure when you're showing your work, it is of course clear and easy to follow. Questions on that problem?
How'd you get the y part?
The y, so if I know what x is, I can plug it into the original equation to find the y.
Oh, okay.
Any other questions? All right, so that's kind of the first application for tangent lines I want to look at. The next application is going to be one that's worded like this. The AP exam loves questions like this. Like I obviously don't see every exam, but most year there's a question relating to this on the multiple choice. Obviously last year was kind of a weird year for the AP exam, but this is a fairly common type of question. So it tells you that the line y equals 6x plus 4 is tangent to the graph of f of x plus x squared plus k. So we have like this unknown, in this case it's a constant, sometimes it's a coefficient, but some unknown number. And we want to find that number so that our graph is tangent to 6x plus 4. Now normally the graph would not be provided, so you can probably look at that graph and figure out what the answer is going to be. I put the graph on here mainly for the instruction of it. But when we approach this problem, I do want to kind of talk about the concept of it so we can think about what's happening here. The first thing that we have happening is that we have this tangent that is y is equal to 6x plus 4. That is just a true statement. We can also see that there is a point of tangency here. But right now, we don't really know the x-coordinate of the point in tangency, and we don't really know the y-coordinate of the point of tangency. Maybe we need it, maybe we don't, but we don't really know where those are intersecting at. We do know that they intersect. And we want to be able to find this constant value for k. Any ideas of how you might start this problem if you were trying to figure out what k is? Or something you would just try to see if it would help you in any way?
Find the derivative of.
Find the derivative.
y.
So we're in calculus. Let's find the derivative. So we see that f of x is x squared plus k, and k is a constant. So let's think about if I wanted to find f prime of x, what would f prime of x be equal to? We have the derivative of x squared, which is 2x.
Just 2x.
Just 2x, because k is a constant, so it goes to 0. So let's think about what we can relate this to. I know that the derivative is equal to 2x, where x basically we know is some value that we can plug in. And we know that at some x value, we actually know what that 2x has to be equal to. What do we know 2x has to be eventually equal to? What does f prime again represent?
The slope of the
Slope.
tangent line.
The slope of the tangent. Well, what do we know the slope of the tangent is?
6x plus 4.
What's the slope of the tangent?
Oh,
Just
6.
6.
Just 6. So let's make sure we don't mix things up. So the first equation we're actually going to set equal to each other is we know that f prime at some value of x is equal to the slope of the derivative. So we're like, if you're the type of person that likes having steps, the first step is to take your derivative and set it equal to the slope of the tangent line. And then often we're going to be solving for x. And that x you find is basically the x coordinate of the point of tangency, meaning the point where the tangent line and the graph intersect. So 2x, we know that 2x for some x value needs to be equal to 6. I know that x is equal to 3. How is that now useful to us? We now know that this graph is intersecting at the value of 3. But we still don't have this k value, so we need to think, well, what can we do to find this k value? This k value is part of the original function. F of x is equal to x squared plus k. Any ideas of what you can do to maybe, using that 3 probably, any ideas of what you might be able to do to solve for k?
Plug 3 into y.
So you can plug 3 in for x to get the y.
Yeah.
So like if I know like this y value is x squared plus k, you can kind of think to yourself, all right, so this is at the x value of 3, the y coordinate of the point of tangency is going to be basically whatever f of 3 is. Well, f of 3 would then be in this case 9 plus k. K is a variable, so it'd be nice if we have an equation that we can solve. What will that 9 plus k be equal to also at 3? Any ideas?
Isn't it also equal to the line like y equals 6x plus 4 if you plug
That
in
you
3?
are exactly correct. So that point of tangency is important, and this is kind of the big idea and where the second equation is coming from. Is you want to set f of x equal to the tangent at the found x value. Because as Anna said, that is the point of tangency. That point is on the graph and it's on the tangent line. It's the only point that is on both of them. So we do know on the tangent line at 3 would be at 6 times 3 plus 4. So this is the tangent. And we can use that to find the k value. So I have this 9 plus k. 6 times 3 is 18 plus 4, 22. That 22 is actually the y value of the point of tangency. But then subtracting by 9, that would then give us this value of k, which is going to be 13. Which you can probably see on the graph, since I didn't take the numbers off, it does make sense. You can see that at the k value of 13, that's a vertical shift for this problem. They are tangent. But that's the main idea that you want to go through. We have two equations we have to kind of solve. For one of them, we had to find like the x value, and then once we knew that x value, we knew that at that point of tangency, the line tangent was equal to the y value of the graph. Any questions or things I can explain a little bit better for that one? All right, so there is one more type of problem that I would normally go over if I had a full class period. It tends to be one that like some students like get and some students don't. But it is something I want to expose to you. So the way I'm going to do that one is I will look at it tomorrow. I don't want to cram too much into one period today. Your quiz is on Wednesday. You won't have a problem like this on your quiz, but I do want to be able to kind of expose you to it. But this is actually where I'm going to go and go ahead and stop notes for today. I'll pick up on this problem tomorrow. Your homework, if I can show it to you, is on the calendar. This is the last homework you have before the quiz. iReady is still a thing being required by the county, but of course now it's not due until this Friday at 5 p.m. Hopefully you've been working on your homework and not getting too far behind. I try to keep this tangent one short, so it's 8 questions. Some of them are pretty straightforward. Find the equation of the tangent line. Page 114 is going to be all of the basic rules, including sine and cosine. Page 125, we're going to have some problems that use the product and the quotient rule. Tomorrow is mainly going to be a review day. I have a brief review I'll do with you, and then I do want to do this last tangent example just to kind of expose you to it. And then Wednesday is going to be your quiz, and that quiz is going to cover curve sketching and then basic rules, product rule, quotient rule, and then tangent lines. So yeah. That's it for today's class meeting. If you are good to go, then I will see